Okay, in the last class we were talking about the mutual inductances, and we have already learned how to model general electrical networks, modeling the elements of the network and modeling the situations like the mutual inductance are now understood. In that situation, we can develop sort of a general technique for handling any electrical network. So, if there is a electrical network consisting of many branches, loops, and suppose it is a very complicated network. Situations like that often happen in, say, power systems. Then the general technique would be first to identify the meshes, identify the open windows, and the charges flowing in those open windows will designate as the independent variables. So, if there is a circuit something like this, or whatever, then all we will do is to say that here is a window, here is a window, here is, and these are the independent meshes, and we will say Q1, Q2, Q3 and Q4. Thus, we will identify. So, the identification of the independent variables becomes rather trivial. Now, once we have done so, then we have to write down the kinetic energy term, the potential energy term, and the Rayleigh function term. So, these three will be taking the general forms, like let us first write the potential energy phi will be first the energy stored in the capacitors. Okay. So, it will be half C I Q I square, okay, and that will have to be integrated over all i's. So, i's are the independent variables. So, these are the i's. So, it will have to be integrated over I is equal to 1 to n. Then notice that these are situations like this, where a capacitor is placed in, basically the charge flowing through the capacitor is the state variable, but there can also be situations like this where a capacitor is shared between two branches. So, that will have to be written as again half, we will have to sum up over something, I will write that later, and it will be sorry, this will be 1 by 1 by C I j. So, this is a mutual branch, this will be Q I minus Q j square, and this will be integrated from j is equal to 1 to how many? It will be 1 less, because I am not considering this self one, it is I minus 1, all right. So, that exhausts the energy stored in the capacitors, plus in the potential term we also have to include the externally applied forces, which are the voltage sources. So, that will be included. So, the voltage sources could be in such a branch, could be in such a branch also. So, again we will have to individually consider them. It will be minus again sum over, this is E I Q I, this is I is equal to 1 to n. There will be one more term which where the voltage source is placed in between two branches. So, that will have to be written as minus again sum over something, I will write that later, it will be E I j q I minus q j, and it will have to be wait, did I write it correctly? It has also to be summed over I, yes. So, I will just insert, it has to have a summation over I, that means it will be I is equal to 1 to n. Similar thing will have to be done here. So, I will just write it once. The first one would be I is equal to 1 to n, j is equal to 1 to n minus 1 or I minus 1, sorry. Okay. That completes the story about the potential. Now comes the kinetic energy T, again has to be written in the same fashion. So, you will have half, it will be summed over L I q I dot square. So, this is the self branches. So, it will be I is equal to 1 to n plus now the mutual branches means not the mutual inductance. I am saying if a inductor is placed somewhere, say here, then it will be half, again it will need 2 summations over what I will write later, it will be L I j q I dot minus q j dot whole square, and this will have to be again summed over in a similar way, I is equal to 1 to n and j is equal to 1 to I minus 1. So, that exhausts the self inductances. There could also be mutual inductances, and mutual inductances will have to be written as m q I q j. So, that will have to be summed over. So, it will be plus half m, m is always I j, between which branch and which branch, q I dot q j dot, right. This will have to be summed over, sorry, again in the same way, not in the same way, this will have to be summed over all i's and j's where I is equal to not equal to j. Okay. So, that exhausts all the possibilities of the potential energy and the kinetic energy. Now, we will have to write the Rayleigh dissipation function R, that will have the resistances in the self branches and the resistances in the mutual branches. So, we will have to write it as half, it will be summed once I is equal to 1 to n R I q I dot square. These are the self branch resistances plus half, again it will have to be summed over twice, I is equal to 1 to n and j is equal to 1 to I minus 1. Then it will be R I j, the current flowing through this branch would be q I dot minus q j dot square. That exhausts the complete thing. So, if you have a very complicated network, you are still able to write the Lagrangian equation exactly in the same way. Clear? Now, it is true that often we do not, in our mind we go this way, but actually when we see the circuit something like this, we identify and then we write down, for example, if I have to write down the kinetic energy of this one, we will say this L1 half L1 Q1 dot square plus half a q l L2 q4 dot square and so on and so forth. Just by inspection we can write. You might have noticed that in this formulation I left out the current sources, right. That calls for a begs the question why. The reason is that the current sources need to be treated a little differently. If we are defining these sources, we define the independent variables as the currents flowing through the meshes, and suppose there is a current source appearing somewhere in one of the mesh, what happens? That particular q I dot immediately becomes equal to that current source. It no longer remains an independent variable. So, the current sources actually offer advantage. Current sources actually offer advantage, and when that happens, when you encounter a current source, you would know that the number of equations that we will really need would be one less. That is why we cannot write down the prescription in the same way, but nevertheless let us look at it how it will happen. Suppose there is a current source like this, here. Suppose there is a capacitor, and suppose there is a inductor, and say only this much. Then according to our prescription, what we will say? We will say that this will be our Q1 and this will be our Q2. Okay. Now notice that Q1 is nothing but Q1 dot is nothing but is I, and therefore Q1 is integral of the current independent current source. So, this is say I over T. It is the integral of the externally imposed current starting from 0 to now. So, it will be integral of say 0 to T. You have we will have to define some other variable, because here I am writing T. It will be I of say epsilon d epsilon. Okay. Starting from 0 to now, whatever current has flown, that is the total Q1. Now, once we have defined this, the rest becomes exactly the same. Why? But because in that case we will write the kinetic energy here as half say L C half L Q2 dot square, no problem about it. We will write the potential energy as stored here. It is wait minute. So, it will be 1 by twice C, but now the charge here is Q1 minus Q2 and Q1 is this fellow. So, we will write this whole thing 0 to T I epsilon d epsilon minus Q2, okay, this whole thing square. And your obviously the Rayleigh term is absent here because you are dealing with a conservative system, and then the Lagrangian function will be half L Q2 dot square minus 1 by twice C, this fellow integral sorry within bracket 0 to T I epsilon d epsilon minus Q2 square, right. Now, if you differentiate, notice that here Q1 does not appear at all, and therefore, there will be no equation in terms of Q1. That is natural, because Q1 has become dependent on an external variable, it is no longer a state variable then. So, can you write down the equation in terms of Q2 then? You will have to differentiate this. This is an independent variable independent of Q2. So, when you differentiate this fellow, if it appears alone, it goes off. So, how will you say? The equation will be first ddt of the derivative of the Lagrangian with respect to Q2 dot, it will be L, can you see? Yes, L Q2 double dot minus, now this fellow just expand it, first it will be this square plus this square minus this, twice this. So, it will have, whenever it comes to be just this square, it will cancel off when you differentiate, and ultimately what you get one term with this thing. So, it will be twice Q2 and this differentiate with respect to Q2, only this remains. So, it will be 1 by C integral 0 to T I epsilon d epsilon. There will be another term which will be on this only, it will be plus, because this was plus, it will be Q2 by C, right. That is how it is. Now, notice that the integral appears in the differential equation, that is natural, because you have externally imposed the derivative of q1. Therefore, if you want to obtain q1 as a state variable, you have to have the integral. So, this appearance a bit uncommon, that is why I did not include in the general formalism, but when you have, then you can always do it like this. Okay. Now, when we were talking about the general formalism of electrical networks, we sort of took a rather shortcut path. You will later realize why I say it is a shortcut path. We said that okay, just identify the meshes and assign state variables to them, but as yet I have not bothered to prove that that will be the minimum set of state variables, and in fact in some situations they will not be. Where they will not be and other things we will deal with later, and that is exactly why later I will also deal with another different method of obtaining differential equations for specifically for electrical networks, because there some additional caution is necessary, but for main run of circuits it can be done this way. Now, let us come to situations where you need to model some kind of a nonlinear element in a system. For example, let us not deal with the electrical circuits now, because one nonlinear element you have already come across, that is a dry friction. So, where you have got a body resting on a dry surface, and if somebody pushes it, then it will initially it will not move, and then when that threshold force is exceeded, it starts to move, and then after that the force due to friction remains more or less constant. So, that is what the character is, and we have already seen that it can be represented by means of a graph something like this, q dot here and a force here, okay, force due to the friction I am talking about. So, that is the character of the, this obviously it is a nonlinear function. A linear function is where it will be a function straight line dependence between the force and the q dot. Here it is not, and therefore it is a nonlinear function. How would we represent that? Now, if a system has this kind of elements, or say suppose you have got a circuit where one of the elements is say a saturable inductor, or the capacitance is not really a linear capacitance, a system where there is a spring, but the spring is not really a linear spring, it is a hard spring or a soft spring. In any case, it is slightly bent, the characteristic slightly bent, not really straight line. What we will do then? The general technique is first assume that it is a linear thing. Thereby what will happen? We will write some kind of, for example this one, we will write some kind of a R. If it had been a viscous friction, we will write R, we will write the equation that way, and then say no, my R is not then a fixed quantity, it is a variable quantity which has dependence on this, then we can write it, we can substitute that dependence into the equation. The moment you do that, the nonlinearity is represented. Clear? So, let us see, let us do a problem with a dry friction element. Suppose we have surface, there is a spring connected to a mass, and where it is being pulled with a force F, and this fellow is a dry friction. This surface is a dry friction surface. Again, in this case, the definition, convenient definition of the state variable would be the Q, where Q is measured from the unstretched position of the spring. That will be convenient, right. So, once we do that, we will write the equation as the Lagrangian we can directly write, because we have already written that once. It will be half m q dot square for this one minus half k q square for this one plus f q, right. And the Rayleigh function will be half r q dot square, and notice that here we are assuming initially that this fellow is some number, and accordingly we are proceeding to derive the equations. There is only one state variable q, therefore, we can write just one equation. The first one would be, in terms of this, it will be, so I am writing the equation directly. It will be m q double dot due to this minus derivative of the Lagrangian with respect to q. So, this will be plus, it will be plus k q, for this it will be minus f plus r q dot equal to 0. So far so good, it is a simple stuff. Now, assume that the characteristic of this thing is represented as something like this. So, here is q dot, and here is what? Suppose you are moving it, it will feel a reaction of mg, and there will be a coefficient, say mu. So, mu mg will be the force created. So, this fellow will be mu mg, and this is a minus mu mg. Convinced? Okay. So, in reality it will be slightly up, it will be slightly up here, and then it drops, but let us assume that it is more or less, this is not a very bad assumption. So, mu mg and minus mu mg here. Now, this needs to be somehow represented here, somehow this fellow has to represent that. So, how to do that? Tell me, how would you do that? R has to represent, instead of, when I write r, I am assuming a function like this, linear function. Instead of that, I have to somehow tell this equation that my dependence is like this. So, how will you do that? This can be done simply by, because what is happening, mu mg is the magnitude and it is plus or minus. So, under certain condition it will have to take a plus value, under certain condition it will take a minus value, that can easily be represented by means of a signum function. So, we can write SGN, the signal function of x dot, I have to write in terms of x dot, is x dot divided by the magnitude of x dot. So, the magnitude cancels off, it is only the sign that remains. Okay. So, that will be obviously plus 1 for x dot greater than 0 and minus 1 for x dot less than 0. right. So, in terms of that, then we can write the equation that we have derived as it was m q double dot plus k q minus f, all that remains the same, but now here r times q dot, that has to be substituted to say plus mu m g, the magnitude, times x dot by x dot magnitude, that is it. Oh, sorry, q dot and q dot, yes. So, this would be q. That gives the equation. So, in general, that tells us that in general, if we encounter a nonlinear element, whatever method of obtaining the differential equation will still retain exactly the same method. We will initially assume that this term is R, L, C, whatever it is, and then substitute the dependence of the R, L, C, whatever it is, on the corresponding state variable. That is how we can obtain the equations for the nonlinear systems also. Fine. Now, the last day I was actually planning to do it as a tutorial, but since we missed it, let me give you some problems which you do at home, but it is to be submitted as a assignment. Tutorial normally I would prefer to do here so that I can supervise, but since we missed one tutorial day, I will give you the problems, do it and submit in a separate copy, remember that. Fine. So, let us take this problem. How will you do this? It is a double pendulum. It is a double pendulum. Assume for the sake of simplicity that these two L's are the same, because I am more interested in your being able to derive it than the unnecessary complications. So, let these two masses be the same, that will make it simpler. So, how will you define the state variables, the coordinates? The two thetas, two angles that uniquely defines the positional status of the system. So, this will be theta 1 and theta 2, right, and then you will have to write the potential energy and the kinetic energy. It is a non dissipative system, so you do not have to write the Rayleigh term. Suppose there is a system like this. So, this problem number 1. Problem number 2, a mass is hanging from the roof by means of a spring, and then here you have a spring and a damper connected to another mass, and this mass is being pulled downwards with the force F of t. Okay. So, how will you attack this problem? How will you conveniently define the variables? Q1, Q2, but that Q1, Q2, how do you define? There are two ways, obviously. You allow it to hang vertically, and then wherever these two masses are, call it Q1 and Q2. That is one possibility. The other possibility is, no, do not do that. You raise this fellow with your hand, so that ultimately it goes to a position where this is unstretched. Hold it there, and now raise this one, so that this one also goes to unstretched position. Call that these two positions of the masses as Q1 and Q2, or as the 0 position of the Q1 and Q2, and measure from there. Both these possibilities are there, and you define according to what you find convenient. Both are the same actually. both are equivalent actually. In one you will have one additional term which will cancel off when you differentiate. How about this problem 3? There are two masses this one is connected by a spring damper arrangement, this one is also connected by a spring damper arrangement, and these two are connected by means of a spring. And say there is a force F pulling this mass. In that case, how will you define the state variables? Again, there are two masses, their positions uniquely define the system's positional status. Then how will you conveniently define that? May not be possible, right. In this case that may not be possible. In the earlier case it was possible, but here since these are two rigid walls, this may not be possible to bring these springs to unstretched position. So, in that case what? Okay, you will bring two of them to unstretched position and allow one to stretch, but okay. When you start it, just define a Q, that means it is already stretched to this extent, and then start from there. And once you define the states, the variables, it will not be very difficult thing to write down the kinetic energy and potential energy. This system itself is not very complicated. Okay, let us give some circuits. Yeah, call them K1. Okay. Now take a circuit. Yes. All right. So, here you have L1, L2, C1, C2. Now, you can say E1 and E2. What will you define as the state variables? Okay, let us add some more complication. There is mutual inductance between these two, oriented like that with the dots. So, how will you define? Simple, Q1, Q2, Q3. And then follow the same logic that I showed. This exactly can be done by that. Fine. Okay. Do you want any other circuit problem, or this more or less gives you practice? You asked me a question that day that in case of the pendulum's tip is being, or the suspension is being moved, then does not it define another state variable? Okay. For that system where the one that was considering at that time, it was independently being moved, and therefore, that does not become a state variable. But suppose that is not a dependent one, take a situation like this. So, here you have a F, and then from here then what? So, you have got a mass in a simple harmonic motion, but it will not remain a simple harmonic motion, because there will be another thing pulling it or pushing it, whatever it is. So, it will be another application of force, but can you see that it becomes then quite complicated stuff. But if you try to write down the differential equations, it will not remain quite complicated, it will be simple. But how do you do that? Let me see. In this case, what will be the state variables? Yes, q may be the position of this one. Now, you can define it as the deviation from the unstressed position. So, this becomes a state variable, say q1, and or maybe you can call it q2, which is theta. Does it uniquely define the positional status of the system? Yes, it does. Notice that one is a translational variable, another is a rotational variable. Generalized coordinate, that is the concept of generalized coordinate. Whatever you want to define as the minimum number of coordinates that defines the positional status of the system, fine. Okay. Now, can you write down now the kinetic energy and the potential energy of this fellow with respect to this q1 and q2? Try this, it will be good. So, this was problem 5. Let us think of a mechanism where you have a rigid wall to a spring, but at this point there is a wheel which is able to move in between this, and there is another guide. So, there is a guide here which forces this thing to move this way only, and there is another guide which forces this thing to move this way only. Okay. And suppose there is another wheel, and these two fellows are connected by and then you have got say a mass hanging here. You see, the mass is hanging here, and you can apply some kind of a initial force to this one to see what will happen to it. As you pull it, this will come down, this will come this way, the spring will stretch, and then it will go through some kind of a motion. How do you write the differential equations for that? What are the state variables? q1 is what? Assume that these two are massless, these two are massless, and then what? Displacement of the mass, say, and then do you really need that?
Actually, I think q1 would just define the system. Q1 variable.
Yes, only q1 will satisfy the requirement, because this position is uniquely defined by q1. So, the task is to define the minimum number of variables necessary in order to define the positional status, and that can be done only with one variable in this kind of system. So, once you have written down that, then you have to q1 may be the displacement something like going like this q, and then on the basis of that you have to specify this, that is it. Okay. Try in a Newtonian way, it will become enormously complicated. Try in a Lagrangian way, it will become enormously simple. Okay. Similarly, you had considered a pendulum where this fellow is moving this way. Can you imagine a system where this fellow is moving that way? Yes, you can always do that. Say like this, you have got a spring and there is a say guide, and this wheel is coming. So, that this is not allowed to move this way, it is only allowed to move that way. And here you have a point of suspension from which the pendulum is hung. So, this is a guide that allows it to move only up and down. In that case, how many variables would you need? Think. Two. Which two? Okay. So, the vertical displacement of not the mass of this point, okay, because mass is here, this is just a point where it is being held. So, point of suspension, and this point of suspension is going up and down. So, you can say this position is one state variable, the other is obviously theta. So, you can say if it is the x coordinate, it is the y coordinate, then this can be simply y from here, and it is possible then to define y 0 as the unstretched position of the spring. This would be problem number 7. Okay. You have done a problem with the spring pendulum. Let us complicate your life a little bit. Here you have the spring pendulum, but at this point what is hanging is a bar. So, yes, you will have to consider its center of mass, and then you need only two variables, though it is a for complicated system. Two variables? No, because if this were not there, then because it is a spring, you would have to consider the radial motion as well as the angular motion. So, for this point you need 2, and again for this one there is another additional angle, 3 variables. You need 3 variables. So, you can say theta 1, theta 2, and again the same way you have to define. As I told you that there are many possible ways of defining this. How you define is your business. In the problem that I did, probably I had taken the vertically hanging downward position as the datum. So, that is one possible way. So, there has to be an say r direction in this side, but how you define it is your business. Okay. How about this? Some of the clocks have it like this: a spring, another spring. So, there are 2 springs and it is able to move like this, and there is a torsional spring that connects a rod. So, this is a torsional spring, this is a torsional spring that also gives a springy effect. So, how will you define in this case? You can say this is K1, this is K2, and this is the torsional spring, say Kr, rotational spring, and then it has a mass m, length L. Obviously, you can define one coordinate theta. What other you need? Okay. So, the position of this, so you can say right. You can write down the kinetic energy and potential energy in terms of this. Will be a little tough, but nevertheless not a very formidable challenge. Huh? What? Oh, problem 9. Oh, okay. I will give 10 problems. The 10th problem is where you have say, do you know how cars are balanced on the suspension? Suppose you have got a car which I am representing by means of a very badly drawn rectangle. Nobody would like to get into such a car, but nevertheless imagine that it is a car. And I will not draw wheels, because all I am trying to depict is that while the wheels move, they are on a bumpy ground. So, the bumpy ground is giving some kind of a force this way, and this fellow is moving. So, that is what we feel all the time when we move in a car. And these act at specific positions where this can be represented, the suspension can be represented as springs. At this stage, I will not make it complicated by saying that these two positions are being pushed up and down. What I will say is, okay, just let it rest and then give a push somewhere here. It will oscillate and move. Okay. Now, it has the point is that you have to find out how many degrees of freedom it has. Obviously, I will need to mention where is the center of gravity. I will need to mention where these two suspensions are. Fine. Let that be given. So, the total length is L, say. Out of that, these two are symmetrically placed. This is L by 5 and this is also L by 5, and the whole thing has a mass m. You will also need the rotational motion. There will be a rotational motion, another degree of freedom. So, you will also need the moment of inertia there. So, what are the degrees of freedom and how is it allowed to move? Just one mass, remember, but the same mass will now have 2 degrees of freedom. It can go up and down, it can also rock like this. Okay. So, in order to define the positional status of this system uniquely, how many variables do you need? 2, one representing this position and representing that, and the elongation of the springs will have to be measured from both. It is not just this. So, but if there is a tilt here, so this particular spring is compressed and this particular spring is elongated. So, that will have to be taken into account in order to measure the potential energy in the springs. So, the problem is that just a bar resting on springs, and if you press one, it will go on doing like this, and that is what we are trying to find out later. But first job is to obtain the differential equations. Clear? Doable? Fine. Wonderful. So, I have given you 10 problems, and that 10 problem solution have to be submitted the next day. No, not tomorrow, next week. I will give you the weekend in between. Now, you have noticed that whenever we were trying to use the Lagrangian method to obtain the differential equation, it always yielded second order differential equations, right. Obviously, m q double dot, that was one term. So, whenever you differentiate the differential with respect to time, the derivative of the Lagrangian with respect to q I dot, it obviously yields a double derivative. But then probably you have also done some courses on numerical methods where you have solved the differential equations. Have you solved second order differential equations? How did you solve? You first brought it down to first order, right. So, obviously then after you have obtained the differential equations this way, you need first to bring it down to the first order. If it is a one second order differential equations, you define two first order differential equations and so on and so forth, and then only you apply those techniques. So, even if you are trying to solve it analytically, then also it is always convenient to have it in the first order form. Though I will not say that techniques do not exist to directly solve the second order equations, there are, but nevertheless, since we are very comfortable, we know the techniques in the first order, the next step will be to bring the equations down to the first order. Normally, how do you do that? You define an additional variable, right? You define an additional variable, and that additional variable will can be anything. Can be what? What you do normally define as the additional variable? Q dot maybe. So, you have m q double dot, you say q dot is something, you can do that. But then that will not prove to be very convenient algebraically. Why? Because it is always m q double dot. So, if you say m q dot is the variable, then it will be algebraically far simpler to write it down. So, in general, that is the technique of deriving the first order equations. We define what are known as momentum as the other variable, not the q dot. That is a standard procedure which will make things very simple. I will show you. So, first we define the Pi. Notice we had Qi and now we are trying to define Pi. What is Pi? The notice what is it? The momentum in the generalized I direction, that is nothing but that is it. Imagine any of the situations that we have come across. Say there is a mass, what was your Lagrangian? Lagrangian had this term m right. You differentiate with respect to Qi dot, it gets that is what Pi is, right. So, we in general define the Pi as this. For the trivial cases where these are you can easily identify, there is no problem, but you will see that the advantage when we when there are coordinates coupled. I will show you. For example, the mass connected with a spring as a pendulum, we have seen that there the kinetic energy contained both these things, the radial as well as the, in that case what is the momentum? Simply we already had the Lagrangian, differentiate with respect to r, differentiate with respect to theta, okay, differentiate with respect to r dot and theta dot, you are right. So, that gives. So, once you have this, you can write then ddt of Pi is nothing but the first term in the equation that we had, right. So, our equation was r not r a. Now, notice this term becomes so you can directly write the first order differential equations. So, your equation becomes so the finally your equation becomes P I dot minus this, right. So, it has this dotted term. So, you directly obtain the first order differential equation. Now, I will illustrate this with examples in the next class. That is all.